Alright, this is first cut of monitor for NoICE for the Foenix F256 board. We'll see how this goes organizationally. The source code for the monitor and the tool are on my GitHub, which is Old Bald Geek and then slash F256-NoICE. There's some description there. NoICE debugger itself is www.noicedebugger.com, and there is complete help here. It's got how to run it. It also has a section on how NoICE works, which explains the serial monitor and that, which may also be useful, although they help just in terms of all the goodies you can do with it. So let's start getting a monitor running. And so here's the NoICE monitor. Fairly standard from the 25-year-old 6502 version of NoICE. And then this one's just been tweaked to work on the F256 junior board using the Merlin assembler. So we've got the magic to get a PGX file. I have chosen to put the monitor right now in the very top 8K of physical memory. It could go anywhere. You just need to figure out how to get it mapped to the physical addresses, and then not use it for your own program. We can get more into that later, but for now I'm at 7E000. So the code is stealth, or there's RAM at F800 in processor space, code starts at F900, and then there's the vectors at FFFA. NoICE has a single memory window, unlike the F256 that has 8K windows. Odd thing for me looking at the F256 is that there's physical memory addressing and there's processor memory addressing. And the correlation between those is whatever you put in the MMU. But that's up to the program. There's no standard, or doesn't seem to be a standard for that. It seems that the very bottom of physical RAM is almost always mapped to the bottom of processor RAM. But that doesn't seem to be the case up at the top. So like the top 8K, if you're using the kernel, is probably going to be mapped to flash. If you're going to map it to RAM, well, you could use 7F800, or you could use 0F800, or 1F800, or any number of other things. So it might be something I just don't understand about the conventions of the F256 project, but this is where we are for now. You can enlighten me later. Have equates for some of the 256 Junior's I/O that is used here, equates for the UART, and then everything else down here is pretty much stock, and you shouldn't need to tweak as you use this for different things. So we can build it. I've got a simple batch file which pretty much just runs Merlin with a -v, and it assembles and it works. I've got a batch file that runs it, which again just uses the Python FNX manager run to the PGZ. You can't see the LEDs on there now. I've turned off the railroad lights that Super Basic and company use, but you can see that the output of the the monitor output from the F256 is now showing the kernel log screen instead of the Super Basic screen. So at this point, okay, we've got a monitor running. Minimize some of this gunk, and I'm going to run a 6502 here. If this was the first time you'd run it, you'd be prompted to select a target communications mechanism. There's two available: NoICE serial for this processor, NoICE serial processor, and then dummy target. which isn't a simulator, just lets you look at memory. I've used it in the past to do like disassembly. Like before I got the board, I used it to poke around a little bit in the kernel just to see the binary images of the kernel. But for now, okay, we're set up for serial protocol. On my machine, it's COM1, 115.2 baud, which is the fastest that is listed in the F256 manual. You can get some oddball baud rates above that, but that would only be if your PC's serial port can support those. So we'll start at 115.2. It's a good deal slower than the 6 megabaud supported by the F256 debug port, but that's pretty limited. It doesn't let you start and stop programs and do stuff. So, okay, so we're here. It's come up, it gives an initial set of registers, sets PC to 0, so we're looking at nonsense here. Of course, we're basically disassembling the MMU and some stuff. The monitor started at 200, so if I can do an unassemble from 200, and you can see how that's the startup code for the monitor. You can do, there's many ways to do many things, so for memory I can dump a chunk of memory, and I didn't specify a size here just because it's trying to embarrass me during a demo. Does a dump. You can use a memory command to do dump, same kind of thing. There's a hex dump, that's why does that. There's hotkeys. So again, I'm not going to go through all of this stuff. You can read the help and just play with it is probably the easiest way to go. Okay, so we got the monitor, we're up and running. So let's look at some of the sample code that you sent, and let's just do that. So line draw seemed to be a pretty decent one. So we've got your line draw. I'll get rid of one of these so I don't confuse myself as to where we are. And you had a build batch file, and basically I turned off here mappy stuff, and this is a Python script I've written. Tells it that the window is at 8,000, run it off of line PGZ, and if I run build, again, it runs through the assembler, then it runs through my processor, which says, okay, there's a memory segment at 200, length is 9AA, and then at 201, there's a 0 length segment, so it's basically a start address. What my Merlin NoICE utility does, two things. One is it generates a set of S records for the file, since NoICE doesn't know the PGZ format. It does S records and Intel hex and some other stuff, but S records are traditional for this class of processor. And then we've also generated a set of I/O definitions. So basically, it's kind of ad hoc. This is all sucked out of the output file, and so it sees that all these I/O things are in the D1000 page. So it makes definitions for NoICE, so you can use if you want to look at this register. You don't have to remember, oh, that's D108. You can type in its name. A whole bunch of those, since you're bringing in a whole boatload of definitions. At some point, okay, so here we're finally in line.s, and you've declared some temporary variables, and NoICE gives them addresses, and then there's a default data. You can specify a data type. This is mostly used if you're debugging C, where it could be int, unsigned int, and so do you want them in decimal, do you want them in hex? The default I put in here for assembler, it just makes them X, which means show them in hex. These were declared as 4 bytes long, so they're X32. Line 0 is declared 2 bytes long, so it's X16, and it just kind of goes from there. Here we have code labels. They don't have a size because they are, they're just labels. And then here we define line 64 of the source corresponds to source address 20 or hex address 201. Anyway, we go with that. Normally you won't be looking at this file. I'm just trying to show you what it does. So let's grab, typically we'll grab the .play the .noi file. And you can either do it off the file menu, play, you can do Control P, or there's the little toolbar icon that's got a little right angle on it like a old school VCR. Actually, I'm old enough, it's an old school cassette recorder. And it's, okay, apparently I've done this one before, so it remembers where I was. And I play it, and and then here we are. So the S record said we started at 201, that was in the PGX, so NoICE sets program counter to 201. And it is showing you the source code, right? The red on the left is the physical addresses from those line commands, but it's overlaying this on the actual source code. If we go to the top, this is just your file. Now I noticed the MAPI that you were using, it generates like this aggregate list file based on all of your sources, and that's workable. But if you find, okay, I've got a bug here, now which source file is that bug in? Whereas here, you can see here in line.s, it's up here on the top line. So we're sitting here, it shows where the program counter is. I'm going to get rid of, been through here several times. This is a watch window. So I'm just I can do a step over that. I can do step over from here. I can press F8. I can also do F10. This shows that NoICE has been around since like the mid-1990s. And I think the debugger I was using then, I don't remember if that was early Visual C or it might have been Zortek. Used F8 for step over, and current Visual Studio uses F10, and don't take away stuff if you don't need to. So I'll step over a nit, and you can see that the monitor from the F256 is now doing pretty stuff here. And I didn't come back. Okay, well, we're probably going to continue this game later. Alright, try to step over. That time it worked. I'm going to step over in it colors. Now we're going to step into Terminate, and you can say we're now in term.s. And okay, we're going to clear the buffer. And now, let me get rid of these and show you. So I'm on a watch window here, and I can say, well, I want to add a watch of term X, and I want to add a watch of term width, and let's add a watch of term pointer. And so I step, and of course we're going to clear term X. Let's put some in there so we can see the clear happen. And I'll just put a value in there. And clear. So okay, it's gone to 0. And you can see when the wedges change, they turn red. And now we're going to set the width. You can tell I ran this before. Let's term height. And let's change this to something different. And so we're at C0. One thing NoICE does not have, for historical reasons, is a step out. Step into is pretty easy. It just means put a breakpoint on the next instruction and then you get there. Step over is basically do exactly the same as step into unless the next instruction is JSR, in which case don't put a breakpoint on where you're going, put the breakpoint on where you come back. For step out of is a little harder just given vagary of what might be on the stack, and so has not been implemented. Could happen, but NoICE is not the most active program in the world right now. And put the title, you can see that shows up. MMU unlock, fill color. And now we got a loop here, and so I'm just going to do a go and it should come back to the loop, and so you can see we are changing color and repeating the loop, so I can do that, and could probably play with some of these variables. Now again, because you've got local variables, NoICE does know line X0. NoICE, you can add, you can't parse this as a magical symbol. So there is that limitation if you're using a lot of the autos. And of course this works forever, and we'll just continue looping. I miss anything? We've looked at watches. We looked a little bit before. This is just a general output window that shows what we're doing. And again, whether you use menu or toolbar or command line is up to you. But I can dump part of page 0 like that. But I've also got a memory editor where I can say, well, show me 0. And the difference here is that if I just start typing, I will put something in. I don't want to, obviously, the MMU is currently mapped. If I type here, I might map myself out of existence, so that's probably not a good place to play. If I go down to the bottom of the stack page, I can edit. You can see those change. If I read them back, it doesn't make sense here, but if I want to, I can show these as 16-bit integers. I can have this chunk of memory updated after each breakpoint. Actually, that might be interesting. Is that going to show anything? Let's change this back to 0. And you recall we had a breakpoint, and the watch is updated, and you can see there that memory location changed. I'm going to get rid of these. Is there a way to freeze one of these? I confess I do not remember. I'll just delete all the watches just so we can concentrate on this. Yeah, you can see that something that's stored at 40 is changing. I say, boy, I wonder what that is. It's 40. And I say, well, let's look at my symbols. Let's list all the symbols. And 40 is line color. Well, by gum, that's what we're looking at is line color. So if I want to, I can now put a watch on line color, and we can see that. And sure enough, it's changing each time around. Window. There you go, float current tab. There. So now my watch window has been removed from the tab bar, and I can move it where I want it. And then if I move NoICE around, it just kind of follows there. So you can kind of make yourself a semi-custom layout. Here we're looking at source mode. If I want to, I can tell it mixed mode. So you see the black here shows the line in your source file. The gray under it shows you that same thing disassembled. If you're, for assembler, they're pretty much one-to-one by instruction. If you were debugging C, one line of C might turn into 5 or 10 lines of assembler, and so you could see what those are. What you can't see here is, this 150 plus bracket, evolves into 96, so it might occasionally be useful. Other than that, yeah, just the NoICE help will get you going. All of this stuff should stay put. If I close NoICE, if I come back in, it's ask the target, where are you? So we're in the same place. Now, at this point, we're just disassembling because he doesn't know your source files. You might have loaded something else or done whatnot. If I reload now, this page 0.noi, okay, so now it restarts you from the top. And you notice the watch window, its position and its contents has been refreshed. It will remember that. It will remember, if we list our breakpoints, it remembers we had a breakpoint there. If you changed your source code and rebuilt, NoICE will say, oh, well, that breakpoint, that address might be a different instruction now, so it will delete some of that context information if you rebuild, just to try and avoid confusing you for that. So let's look at your bitmap 256 sample. And if I do a build there, now here you can see, I put NoICE at 7 F800. Now in this case, you put your bitmap at 7, starting at 0000, and you've got, it's about 62 K. So there's room, there's a few hundred bytes room between EEC2 and FF80. Obviously, if this bitmap got 500 bytes bigger, there wouldn't be room. So at some point, either you could change your source to have this on a different page, or you could move the monitor to a different page. But it's not clear that there's one page that's going to work for all possible mappings. But we'll start there. And say, okay, so I want to grab, whoops, sorry, hang on a second. I just squirked myself here. And so let's load, or let's play the bitmap. And now this is going to take a long time because you've got about 62K of bitmap to load, and this is definitely 115K baud is not the same as 6 meg, but it's kind of where you live with serial ports. So again, we're in bitmap.s. I'm not sure there's much else to see here, but I'll put to a string. It's like I can set a breakpoint, get to the breakpoint. If I want, if I just right click, I can say go and tell line, and it will automatically set a breakpoint, go there, and then stop, and then remove the breakpoint. So if it's just a onesie, you can do that. We probably don't want to sit on that loop, so we'll go till here. Some more text. Oh, that's an interesting. Oh, okay. So you can see what's happening here. This is a limitation, as you're doing a branch to yourself. And the way NoICE breakpoints work is it says, okay, well, what's the next instruction when this instruction executes, what's next? Now, for most instructions like load A, well, the next instruction after that load is 2 bytes on for a 2-byte instruction. For a branch, well, or for a conditional branch anyway, if the branch is taken, well then, the next location is here. If the branch isn't taken, well then it would be the following word. So if it was a branch not equal, where it might branch or might not, NoICE doesn't try to figure out which way you're going to go. It sets 2 breakpoints there. In this case, so it says, oh, the next instruction is going to be at address 2D4. Okay, but we're at 2D4. If I put a breakpoint there, then there's no opcode for branch, and so we're kind of stuck. And so you get that error. So basically, you can't you can't set a breakpoint on yourself. That actually brings up one of the remaining issues. Is this a good time to do that? Yeah, it'll do. Is if I just tell it to go now, I have no way to stop it, right? The processor's just going to sit and spin forever here until I do a reset. If we're on an HC12 with PDM, there's a background command that says stop the target. I don't have that here, because there's no way the monitor, the monitor's not in control. It can't do anything. 2 ways to do that, or to deal with that. The one that is the easiest, or that I've used in the past, is if your processor's got a non-maskable interrupt, which 6502 does, and if you're not using it, which may or may not be the case here, you put a bash button, a button, not Linux bash, on that, and if you need to stop, you press the physical button. It causes a non-maskable interrupt. The handler for that takes you back into the monitor and shows you what was going on. So that's one possibility. The other thing we could try would be to, the monitor right now is polled on the serial, but you could make interrupt-driven serial, and then say, if I press the stop button, send a message, and then the monitor, the interrupt would happen, and the monitor would say, oh, character or message has come in and says stop, I'll stop. And that would work, but only if the code you're debugging has interrupts enabled. Well, you can see here, the code we're debugging has interrupts disabled. So I personally have found the non-maskable interrupt useful, just because it doesn't depend on interrupt state. Your mileage may vary. We can figure out how to do that later. Okay, so we've done that. Let's look a little bit, just in case you're interested, and if you're not, you can skip this part, at our text processing utility. It's just a fairly rot-gut Python processor. And so it basically loads the output text file. So if I look at here in bitmap, you've got the big old text file here, and it's got things like, well, what file did this come from? What kind of line is it? And got too many files open here. Please stand by. Let's see. I think we don't need the monitor. Let's close that. And yeah, here we are back in the land of Python. And so it loads that. This is a command that tells NoICE to scrub old debug data, and we just read the lines one at a time from output.txt. And remember what we're looking for. So, if it looks at the file column to say, has the file changed? That's a NoICE command that associates line numbers. In some cases, I don't think you can do it here, although it might be interesting. NoICE supports the difference, but you can have global symbols and labels, or you can have scoped ones, again, mostly for C, where a variable could be global scope, it could be file scope, static, or it could be function scope static or block scope static. Those last two aren't really true in assembler, although file scope is somewhat useful. Now with Merlin, which when it assembles, I'm used to old school assembly, like when I was writing assembly back in the 90s or 80s and 90s, was you'd have multiple object files. Each of your source files would generate an object. You'd link them together just like you would with a C program. So Merlin doesn't do that. It gloms all of the source code together and then assembles it as one blob. But as near as I can tell, that means that any symbol or label that you define in one of those files is going to be global and seen by all of the other ones. If that's not true, let me know. But right now, we're doing definitions that it just assumes are global. So again, okay, if the line says code, if I can stretch this, we get down to, so here's actually some code. And it says code here, and it's address 201, and there's 3 bytes of data there. And so basically he says, okay, well, if the line is code, then we can define a symbol. If there's a symbol, oh, here it is, code. We define the line with the address that we read from there. Our file is wherever we are. Some lines will have labels like start. Apparently in Merlin, labels have to begin in column 0, which is pretty limited. I'm old school DEC PDP-11 assembly, and you put a colon after your label and you start wherever you want, but this is the religion we have now, so we go with it. So again, we can define labels, get defined here. This is kind of a hack. Labels have to be in column 1. For I/O symbols, the name starts in column 1, but typically you get a lot of noise in your in the label and I/O definition, because you may define, foobar mask has a value of 5. Well, it's not address 5. It's a bit pattern that you're going to use for something. So just kind of as a ad hoc thing, if it's an equivalence, an EQU, or then it says, okay, if the value is in the range C1000 through DFFF, then I'll say, well, this is an I/O equate. I'll assume that most programs are going to keep I/O mapped in that range. Certainly not always true, so this maybe could be made optional. But if it's in there, then I'll define that as a symbol so that I can do watches and stuff on I/O devices. And the other thing I'm looking at, okay, if you've got a label or a symbol and it's up in the kernel range, right now I don't generate a definition for noise, but I put out a warning, say, maybe this code is using the kernel, and we've got the noise monitor up at E1000 to FFFF, so this code may not run. Again, this is all provisional until my next plan of work is to get NoICE to work with the kernel, either in RAM or in Flash or both. But for right now, that's our ad hocness. Okay, once we've gone through the output file, we then load the PGZ file and generate S records, either for a PGX or a PGZ. And that's done up here. And I've got here kind of, again, this is a hack or a short-term thing, is if the physical address that you specify, or if the region you specify, address plus length, falls inside the monitor range, then it doesn't generate an S record. It says, hey, look, you're overlapping the monitor, so I'm not going to output that. You're not going to be able to debug this. And then that would be a sign you either need to move the monitor, and change, right now I've got this hard-coded here, probably should go in an INI file. The way the loader has an INI file for default, so either as a command line switch or an INI file or both, and then you could either turn that off or change it to whatever. And then again, if the address is above 65K, we generate Motorola S2 records. If it's below 65K, we generate S1 records. Just as a quick and dirty, because I hate doing byte processing in Python, I don't generate a checksum. NoICE ignores the checksum because checksums are there to deal with communications errors, and if you have errors in files coming off your hard disk, you got bigger problems than a checksum is going to correct. So that's the text processing. And again, for TAS or any of the other assemblers that a person might want to use, there'll be similar routines or similar utility functions written. I'm just using Merlin because that's what your examples use. It looks like I'll be getting into the others as we get into kernel land. So to-dos or outgoing stuff yet, is that the local labels as produced by Merlin, they don't generate symbols visible to NoICE, so if you're looking in source code mode, again, and typically you're setting your breakpoint by double-clicking on a source line. You don't need to know the address, but potentially annoying. We talked about forcing the target to stop. NMI is where I'm going to look. I do notice the F256 manual, hardware manual, says one place NMI isn't used, but the description of the IEC serial port has a bit that says it turns an IEC interrupt into an NMI. And so my next set of experiments, at least if I can find an appropriate DIN plug, is going to see, could we hook up a button to that and use that as a bash button, since unless you really have a Commodore disk drive that you need to plug in there. You can go possibly directly to NMI, but this note here implies that there's some gate someplace pushing it, so probably don't want to short that out. And also NMI is edge triggered, and so you need some kind of debounce on it so you don't bury yourself in a million NMIs. But that's first thing to look at. I talked before, the serial interrupt could work, but you have to have interrupts enabled, which is kind of a pain. Figuring out how to work with kernel. I'm not sure, I didn't notice any of your samples using the kernel. A couple of them seem to bring in source files of the kernel and link them in separately, but I'll need to play with that on different assembler and learning more about the kernel. To do that, then there's the question as well, where does the NoICE monitor go? There's actually plenty of room. The monitor, as you saw, is only a little over a K. There is right now in the top 8K of kernel, there's that much space. We could tuck the monitor code itself in Flash there, because it needs to hook into the IRQ vector so it can look for break. Or we could hack the kernel so that it looked for break, and then if there's a break, pass that out via some kind of RAM vector. Second part of the getting NoICE merged in there, the code could live in Flash, but it's somewhere 100 to 200 bytes of RAM for the monitor's buffers, and where do those go? And there again, I need to look at the kernel source code to just see what is the RAM layout used by the kernel, and is there a place I can safely put stuff? I could map a whole nother 8K chunk, but again, then you got to worry about keeping that safe from user programs. So we're there, and then other assemblers we already talked about. So I think that's we'll call that good for now.